Up next, we have Dr. Lilly Chin. Dr. Chin is an assistant professor and a Texas Instrument Jack Kilby Fellow in the Chandra Family Department of Electrical and Computer Engineering at the University of Texas at Austin. She is interested in designing robotic bodies and their materials for optimized interaction and their environment through embedded perception and computational design. Dr. Chin received her bachelor's, master's, and PhD degrees in electrical engineering and computer science at MIT. From 2023 to 2024, she worked as a Schmidt Science Fellow at the National Institutes of Health under Leo Cohen and Tom Bulea. She is the recipient of several fellowships, including the NSF Graduate Research Fellowship, the Hertz Foundation Graduate Fellowship, and the Paul and Daisy Soros Fellowship for New Americans. Please join me in welcoming Dr. Lilly Chin.
All right, thank you for the introduction, and it's great to talk to you all today. I'm here to talk about how material matters, designing robot bodies and dialogue with computation. So oftentimes when we think about robots, we're often thinking about the body just as a vehicle for the brain, right? This like classic cartoon drawing of like a brain in a jar. And we see this when we look at the different robot bodies that exist. They're either sort of a box on wheels, a metal arm. We've seen a lot of humanoids today, but they also have a similar pattern of just metal and these linkages. But what if we start thinking about the robot as more than just a vehicle for the brain? Here's an example from Unitree, where they start thinking about, instead of just imitating a dog, what if we have a quadruped with wheels on it? And if you can see in these demonstrations, changing the body really gets into these new dynamic applications. We have the speed from wheels with the suspension of legs to really do these dynamic applications. So I'm interested in seeing if we explore how the body can really work with the brain to get newer applications. And for an everyday example, like in manipulation when you're cooking, right? The speed with which you can chop onions or the fluidity with which you can saute vegetables, these simple skills that you do every day are just not present in current robots. What I argued that we should do instead is have the robot body complement the algorithms. Instead of having like a brain in a jar that just gets carried around everywhere, what if we take inspiration from, say, reflexes? If you move close to a candle, you feel pain from your sensory neuron. This gets transmitted not to your brain, but to your spinal cord, allowing for a really fast reaction time, sending a signal to your motor neurons. So in this case, right, computation is embedded throughout the entire body. I'm not the only one who's thinking about this approach. As part of Science Robotics' Grand Challenges, some fellow roboticists said this: sensing, actuation, and computation are the basic principles of robotics. However, rather than using discrete components for achieving these functionalities, the major challenge is to fully embed them in the material itself. In other words, right, instead of we have sensors and a CPU and some motors, what if we incorporate them all together into the body? Materials have been labeled #1 in the list of Science Robotics Grand Challenges for this reason, and I think it's a really interesting space that we should explore more. So this is what my lab studies, Merge Lab, and we're studying how materials embody robots geometrically. Our lab's core focus is on sensors and actuators. So for sensors, we have this really cool way of 3D printing internal tactile sensors inside the body of robots. And on actuators, we have these really cool body designs that combine twisting with extension and expansion, expanding the ways that robots can exist in this world. To build these sensors and actuators, I draw from a lot of different fields as part of fundamentals. I'm inspired by the way that people with disabilities change their environment around them to better suit their own bodies. I'm also inspired by mathematics and looking at the ways that geometry can play a cool role in designing new bodies. So with these fundamentals and applying them to sensors and actuators, some of the applications I'm interested in include medical devices and robot manipulation. So in medical devices, I adapted some of those 3D printed sensors in for pads on an exoskeleton brace. So as this person is walking with the brace on, we can get a sense of the net moments that they're exerting on the exoskeleton. In robot manipulation, I've been interested in combining both the actuators and the sensors to have a fully proprioceptive robot manipulator. So our key approach through all of these different areas is to embed functionality into the material's geometry. I don't have enough time to go in detail, but I'll give you the highlights. I'm going to be talking as geometry as sensors, these 3D printed tactile sensors, Geometry as actuators, talking about auxetics and how we motorize them to get all the cool movement you saw, and then combining the two of them in order to make proprioceptive materials. I'll be focusing on geometry as actuators first, so this idea of auxetics. Normally, when you pull on a rubber band, it gets skinnier, right? But auxetic materials, the opposite happens. When you pull on them, they get thicker. This doesn't exist in nature at all. You have to create new geometries like these rotating squares. Here's an animated version if you're more of a pictorial person, but you can see how the white and black squares are rotating against each other. So it starts off small, but then as the rotation happens, it expands to this larger material. That's what auxetics are. So there's some kind of fun geometry that creates this expansion in systems. We're not just limited to the 2D case. If you've heard of Buckminster Fuller, the guy who made buckyballs, he actually made this toy also on the right. It's called the jitterbug. And you can see the same thing as how the triangles are rotating against each other to create this expansion of motion. So what I did is we took like Buckminster Fuller's toy and made robotic versions. On the left, we have one that's more optimized for force, and on the right, we have one optimized for expansion speed. So you can see on the left, this video isn't sped up, but it's got this really dynamic motion to it. Each of the modules are expanding. It's the same squares rotating against triangles. And because we're using the geometry for our advantage, that has a strength to weight ratio of 76 times. When we compare this against other modular robot locomotion, we're nearly 10 times faster, again, because we're exerting quite a bit of force and are able to expand so large. If we look at the expansion speed-focused ones, almost immediately you see there's almost this explosive motion. Out of the modular soft robots we surveyed, we had the fastest expansion speed, expanding 1.57 times our radius in 0.2 seconds. This is able to impart a really high impulse force, and then if I've timed this correctly, this next one will allow it to flip over. So we're kind of getting more dynamic motions than we're used to with modular robots. So this is an example of how we can use geometry to achieve new and better performance. I also changed the pattern of this auxetics. So instead of having regular squares or triangles rotating against each other, I now have rectangles and sort of tilted on the cylinder. This is cool because it connects twisting with extension. So here you're going to see this 4 degree of freedom robotic platform moving through these motions. So we've arranged these cylinders in this checkerboard pattern, and by actuating any 2 of them, we get bending from side to side. Actuate all 4 of them, they extend, and then here it's twisting in on itself. So again, using geometry to our benefits, we can extend up to 60% of our original length, and we can bend up to 100 degrees on either side, or twisting in of itself to 3/4 of rotation. With a simple change in the geometric pattern, we can turn it instead from this up and down motion to a bending motion. So we can now start to think of this as a robot gripper. In fact, when we compare it against standard soft robotic grippers that are pneumatically driven, ours is 20 times more power efficient and twice as fast at opening and closing as a gripper. I use these fingers as the basis for many different applications. Since we're not using pneumatics to drive it, we are puncture resistant and we can do recycling sorting. The hollow structure of our actuators means that we can put in suction tubing inside, making this cool gripper that combines parallel jaw grasping, soft finger grasping, and suction. There's the suction example. And then finally, we can just use these fingers as a normal soft robotic gripper. So we used this compliance and applied it to a grocery packing situation. So again, geometry is opening up a wider range of different applications, different systems that we previously wouldn't have thought about. I'm now going to transition into sensing applications. So in the inset, you can see on the right, that looks like a regular 3D printed system. But if you had X-ray vision, you would see what's happening on the left. So inside this black lattice, we have these empty air channels represented by blue. So we print this structure with air channels inside so that if we seal up one end and measure the pressure, as the system is deforming or we're poking it, we're going to be measuring a change in pressure. So in this example, we're going to be moving the little lattice from side to side, and you can see the sensor performance in the bottom right. So what's really awesome about this is first off, it's acting like what we expect. You move it from left to right, the left sensors activate first before the right. But also, especially in this region where we're doing some really fast movements, our sensors are able to keep up. We're not having to worry about time delay or hysteresis. We can just capture all of the signals that are there. So this is in deformation, and we're also doing the same thing. In this video, we're going to be pressing from left to right. And we see the same behavior that happens here. First, the left sensors are active, then the middle, and then the right. And even if we're doing this very fast tapping, we're able to capture this behavior, even seeing that, oh, we're actually pressing more on the third press. This is really awesome. So we're going to be connecting these two into one system. So here is the 4 degree of freedom robotic platform that I showed earlier. And in the inset, you can see how we have these empty air channels inside the structure. So now as we put the robot through its paces, right, I want to emphasize these are raw sensor inputs. I didn't do any filtering to these at all. It's coming in from a very clean signal because we're measuring the air in the channels instead of any soft materials. We were able to collect the largest robotic data set, about 18 hours, helping this method be good for machine learning applications. And through a simple LSTM network, we could estimate pose to within 8% of position and orientation. So hopefully I've convinced y'all of that we should start thinking more about robot bodies, both in material and geometry, as I talked about geometry as a sensor, actuator, and robot. I'd like to thank all of the collaborators who made this possible. A lot of work went into this, and happy to take any questions.
Y'all are doing some really impressive stuff with the robotic grippers in regards to recycling. Are y'all able to bring that out of the lab much at this point?
No, we weren't able to bring the recycling out. I recognize that now I've learned more about recycling, it's a very hard problem. And so if anyone's interested, let me know. Yeah, okay. Yeah.
Okay.
Do you use a lot for kind of confined space locations where you really can't get a big robot into? Is this a potential application you're looking into?
Yeah, for my interest, I've mostly been focused on manipulation, just to solve the initial grasping problem. I don't have personally much field robotics work, so confined space would be interesting. Yeah.
Thank you. And I just wanted to ask, because you were doing it all with your fluid, right? Your working fluid was just air for all of it. Using an incompressible fluid, would you imagine that would improve on the signal fidelity, I suppose?
Yeah, a lot of folks have asked about whether instead of filling it with air, we fill it with something else. We've been interested in air just because we can print it and then we're done. I think doing magneto-rheological fluid or something else that you could get new actuation, maybe liquid metal, that could add an extra element. So thank you.
Yeah, very cool.
Is all your printed stuff, is that all laser sintered? Is that how it's done? Or what kind of technology do you use to print these fine structures?
Yeah, so actually everything on here, this was done on the Carbon 3D, which is a very high-end resin printer. Over my postdoc at the NIH, I got it working on a Formlabs, and my undergrads right now have been getting it working on TPU on an FDM printer, which I'm also very shocked by this, because I didn't think that's supposed to be airtight, but we're now exploring that, because I'm very excited that instead of a $150,000 printer, we can start getting this on a $100 printer. Yeah.
We have time for one more question.
Thank you. This is really cool work. As you're changing the shape of your manipulators, do you worry about changing impedances? Like you're changing the geometry, how does that affect the stiffness of your finger grippers?
Yeah, so definitely, right, as we're extending it, there's now a lot of air. So we think that this is a benefit because it's more compliant. but it's also the little flexure joint that's causing all the geometry. That's the point of failure. So I'm interested in applying computational design to this to sort of optimize what that flexure could be, because all of the designs you've seen is me like trial and erroring, like figuring out what that should be. So I think it's particularly rich, especially because these are all repeated lattice designs. So I think that should lead into faster optimization, since you don't have to repeat, you can repeat the pattern. Yeah.
Thank you so much, Dr. Chin.